Okay, so in this session we will prove Fubini's theorem, which allows us to interchange integrals for a class of functions, in particular for positive functions. So if you look back at the statement of the Fubini's theorem, we are not for positive functions we are not saying that the integral should be finite. Whenever you have a positive function on a product space, it is possible to integrate in whatever order you want. Okay, so that is the content of Fubini's theorem. But if the function is in the L1 space of the product measure, then of course the integrals will be finite. Okay, so we will start with the proof now. Okay, so proof of Fubini's theorem. So the proof follows exactly in the expected manner, because for sets we have already proved this. Okay, so let's recall the statement of the theorem. So we'll look at the statement A first. And if you look at the statement A, you see that the function phi and psi which we define for sets, and we have shown that these integrals are same, right. So this is true whenever the function is an indicator function. That is precisely the content of the construction of the product measure. So let us start with that. Suppose f is equal to indicator of q, characteristic function of q, where q is a measurable set, right. It's an arbitrary measurable set, it need not be a rectangle. Our construction of the measure, so our construction of the product measure mu cross nu, right. So this was on x cross, so this was on x cross y comma f cross g, right. This is our product measure. This shows that, well, how did we construct this? This shows that if I look at q sub x, okay, and then you look at nu of that measure, that set, you get a function which is measurable, and then you integrate this function over x with respect to the measure mu. Okay, this is same as integral over y mu of q super y d nu y, right, which is what we called mu cross nu of the set q, which is integral over x cross y, indicator of q, well, I will write x comma y, and you have the measure mu cross nu, right, x comma y as the variables. This is what the construction of the product measure is. But what is this? So let us rewrite this. The left hand side is integral over x, this is integral over y, indicator of q sub x at y, right, d nu y. So this would be the measure here, right, and d nu x. Of course this is equal to integral over y, integral over x, chi q super y at the point x d mu x. So that would be the inner integral, and you have the outer integral with respect to y. But what are these chi q sub x y? So chi q, so let's try to write it down. What is chi q sub x at y? Well, this will be 1 if y is in q sub x, 0 otherwise. Okay, and you see that this is actually equal to chi q of x comma y. X is fixed, right. So it's just a section, and that is all is needed. So if I plug that in the previous, so you use this here in the previous equality, what we have is integral over x, integral over y, chi q of x comma y, d nu of y, d nu of y, d mu x. What we are saying is, you do the same thing here, you will get that it is integral over y, integral over x, chi q of x comma y d mu x. So now you are integrating with respect to x first and then integrating with respect to y, which is of course finally equal to lambda cross, sorry, there is no lambda, that's mu cross nu of q, right? And that is the statement of the theorem. So measurability, so this is measurable follows, right, that we have already proved. So for indicator functions this is trivial, okay. So from characteristic functions, so from chi of q we can go to simple functions, positive non-negative simple functions, using linearity, right, linearity of the integral. So what I mean is, if I have this equality for f equal to chi q, I can replace that with summation alpha chi q I x comma y I equal to 1 to n, right? And then because everything is linear, this will become a sum of things, and that each term will be equal to the corresponding integral in the other order, and so on, so forth. So I will leave that to you, okay. So this is a trivial step. Now from simple functions, we go to positive functions, positive or non-negative measurable functions by taking limits, right. So this is a standard method which we have seen earlier, taking limits. So let's see how to do this. So we need to define some more functions, okay. So let f be positive, and it's f cross g measurable, okay. So it's on the product space. So there exists simple functions, 0 less than or equal to Sn less than or equal to f, such that Sn increases to f, right. That is one of the basic results. So we have this. So you can define phi n. Well, what is phi n? It's a phi function associated with Sn. So phi n of x is integral over y Sn sub x, right, d nu, right. And similarly I have okay, so let me write it here, because then I can show you how the limit is. So we write it here, define phi n of x to be integral over y Sn sub x d nu, and we look at psi n of y to be integral over x Sn super y d mu, right. So these functions, so Sn's increase to f, so the sections also will increase to the corresponding sections of f, right. So Sn increases to, so let me write it here, Sn increases to f, so Sn sub x will also increase to f sub x, and Sn super y will also increase to f super y. So you apply that, because Sn, so we know phi n's are measurable. Well, how do we know phi n's are measurable? Because Sn's are simple functions. Simple functions are linear combination of indicator functions, and for each indicator function we know it is a measurable function. So phi n is simply linear combination of measurable functions, so it is measurable. Similarly psi n's are also measurable, okay. Now apply monotone convergence theorem. Well, why am I applying monotone convergence theorem? Because I know that there is some increasing limits here, right. So and they are all positive, so apply monotone convergence theorem. This will increase, right. increase to integral over y f sub x d nu by monotone convergence theorem. Similarly, this will also increase to integral over x f super y d mu. Okay. So, if I call this phi of x, so phi function for f and this to be psi of y, then phi and psi are measurable because they are increasing limits of phi n's, right. So, apply because limit of measurable functions. Okay. So, this was one of the assertions, but you can apply monotone convergence theorem again. Well, where are we applying monotone convergence theorem again? Well, I know that phi n's increase to phi. So, integral of phi n's should increase to integral of phi by monotone convergence theorem. Psi n's increase to psi. So, that should happen with psi n's as well. So, apply MCT again to get integral of x, integral over x, phi n x d mu x. This will increase to integral over x, phi x d mu x, right, and integral over y, sin y d nu y will increase to integral over y, psi y d nu y by MCT again. But at the phi n level, we know the equality, right. The iterated integrals are same for symbol functions, right. So, from chi q we can go to symbol functions using linearity. So, we have the iterated integrals equality for symbol functions, right. So, iterated integrals are same for symbol functions by the previous step. Okay. What does that mean? That means integral over x, phi n x d mu x is same as integral over y, sin y d nu y. Well, they are iterated integrals are same to the total integral as well, right. So, this much we know, x cross y, this would be Sn d mu cross nu, right. Phi n and psi n are defined for Sn by taking sections. Now, I know that this one converges to integral over x, phi x. So, phi x, so I will write one more step just to be clear. Phi x, phi is the function defined for f, which is same as, I know this converges by monotone convergence theorem to psi y d mu y. And well, what happens here? I have the space x cross y and I have a countably additive measure, and I know that Sn increases to f. So, I can apply monotone convergence theorem again here. So, MCT saves the day. MCT here says that x cross y f d mu cross nu. Okay. So, now I can put together everything. So, let me write it in full detail. What was phi? So, let's recall phi here. Phi of x was integral over y f sub x d nu, and psi of y was integral over x f super y d mu. So, you write that. So, this would be integral over x. Phi is an integral over y. So, integral over y. F sub x at y. So, that is just f of x comma y, right. And you are integrating with respect to nu, that is with respect to the y variable. And then you integrate with respect to, that is your phi of x, and then you integrate with respect to the x variable. So, that is same as the next integral is integral over y. Psi is an integral over x. Again you will have f super y at x. So, f super y at x is f of x comma y d mu x, right, because you are integrating with respect to x first. This is same as integrating with respect to so iterated integrals are same, but more importantly they are all equal to the total integral of f, x cross y f d mu cross 2. So to compute for a positive function the total integral, you can do the iterated integrals. So that is the first part of the theorem, right. So let's go back to the statement. So this was a long statement. We proved A, right. For f positive we have measurability and the iterated integrals are same, equal to the total integral. So this is what we just established. Let's look at the complex valued case. Complex valued case, well, simply follows from the first statement. So let me indicate that. So I'll leave the details to you because it's sort of straightforward now. Okay, so we can start here. So for B, apply A to mod f, right. So mod f is positive. So mod f is a positive function. So A applies, right. So A can be applied. So if A applies, what does it say? We will get that if you look at mod f, the x sections, and you integrate with respect to y, that is the phi function for mod fx, right. So I will write this as d nu, and then you integrate with respect to x d mu x. This is same as integral over y, integral over x mod f super y d mu and d nu y. This is same as integral over x cross y mod f d mu cross nu, right. So it's enough to write it. So this is true for mod f because mod f is positive. So let's write it in the proper form. So this is simply integral over x, integral over y mod of f of x comma y d nu y d mu x equal to etc equal to integral over x cross y mod f d mu cross 2, right. So I am not writing the whole detail. So that's all the second statement is. So that's the interesting part of the theorem, because you can always take mod f and then apply iterated integrals and see if it is finite, right. So if that is finite, if any of the iterated integrals is finite, then f will be in L1, right. Any of the iterated integrals of mod f is finite, then f will be in L1 of the product space. So let's look at C. In C you are starting with an f in L1 and you are saying the iterated integrals are same, okay. Iterated integrals are same. That is what we want to prove, okay. So this is not difficult, so I'll try to give the details, but maybe only the sketch of the proof, because it's not very difficult. The first part is the main part, okay. So see, for this, so first assume, or okay, so maybe enough to do this for, so enough to prove this for real valued functions, real valued f can be complex valued, that is by linearity, right, linearity, because you can always write f as u plus iv, and if the iterated integrals are same for u and v, it will be same for f as well, right. So assume f is real valued. So I can write f equal to f plus minus f minus, right. Remember the positive part and the negative part. So what is f plus? F plus equal to maximum of f and 0. So whenever f is 0, f is positive, it is f plus, f is negative, f plus is 0, and f minus is maximum of minus f and 0, right. Wherever f is negative, you take the negative of that will be your f minus. So both are positive measurable functions, right, okay, and f is equal to f plus minus f minus. So also notice that, well, what is mod f? Mod f is f plus f minus, okay. So this also tells me that hence f plus is less than or equal to mod f, comma f minus is less than or equal to mod f, but f is in L1, right. So since f belongs to L1 of mu cross nu, anything, so mod f will have integral finite, right. So this will tell me that both f plus and f minus are also in L1 of mu cross nu, also they are positive. Okay. So A applies, so A and B if you want, A and B applies, and iterated integrals are same for iterated integrals are same for f plus and f minus. Okay. So I'll write it instead of bringing in phi and things like that. Let me write it in one go. So I look at f plus of x comma y with respect to d mu x, right. So first integrate with respect to x and then integrate with respect to y. So that would be same as the integral over x integral over y f plus of x comma y d nu y and d mu x, right. Similarly for f minus, okay, f minus, and both of course are equal to the integral of total integral over x cross y. Okay. So I'm not writing that. So but maybe let me write this portion, because I'm going to subtract d mu x d nu y integral over y equal to f minus of x comma y d nu y. So first integrate with respect to y and then integrate with respect to x, right, d mu x. So these two are same for both f plus and f minus because they are positive functions in L1. So the first two cases apply. Now all you have to do is to subtract these two. So there is some measurability part which I am skipping because it should be clear to you that what is measurable and so on. So all you have to do is to subtract these two, right. So remember that both the integrals are also same as, so this is equal to integral over x cross y f plus d mu cross nu, right, and similarly this is same as integral over x cross y f minus d mu cross nu, right. That is the first and second part. Because of this, subtract to get the result for f, right. So you have to so you have to make sure that when you subtract you are not getting an infinity minus infinity term, but these are all in L1, so they are all finite quantities. So these are all finite numbers, okay. So finite positive numbers in fact, because they are all positive. So I can subtract them and then I will get, so if I subtract I am going to get integral over x integral over y f plus minus f minus, that is my f, right, f of x y d nu y d mu x equal to integral over y integral over x f of x y d mu x and d nu y, which is of course equal to the product, the full integral, right, f d mu cross nu. Okay. So I am writing the same thing again and again. You can subtract because they are all finite. Okay. So there is one small thing which I have skipped, but that is sort of trivial, so I'll leave it to you to think about it. That is the, so let us go back to the statement. Yeah. So we have this and this, they are measurable and they will be in L1 because their integrals are finite, right. So we have just proved that if I look at the plus part and the negative part, then the integrals are finite. Okay, so we will stop here. The proof of Fubini's theorem is rather simple, but it requires you to construct the product measure first, and the construction of the product measure essentially tells you Fubini's theorem for indicator functions, and then from indicator functions you can go to symbol functions and positive functions. Once you do it for positive functions, you will have it for all other L1 functions by appropriate linearity and things like that. So that is what we have done. So the upshot of all this is, if you have a positive function, the iterated integrals are same, or if the function is in L1 of the product space, iterated integrals are same. Okay, so we will stop here.